Next, let's talk about transformation. Transformation, what's the motivation for transformation? We have a random variable x. We know its distribution. We are interested in a random variable y, which is some transformation of x. So you know everything about x. Now, I would like to know the distribution of y. The y is gx. For example, if g is 1 to 1, so if this transformation is 1 to 1, this is very easy. I need to calculate the distribution of y. So for the discrete case, so I need to know the PMF for this y. Now let's calculate PMF. You give me a little y, I calculate probability y equal to little y. What is a big Y? It's a transformation of x. So this is gx equal to y. Since g is 1 to 1, it has the inverse. So it's x equal to g inverse y. Since I know the distribution for x, I just plug in g inverse y to the PMF of x. Now I can get the distribution for big Y, this transformation. For example, I said let x be the flip number on which the first head appears. Now y be the number of flips before the first head. Now we can, x and y has a relationship. Y is a transformation of x. So in this case, gx is x minus 1. So if I know the distribution for x, now I can get the distribution for y easily, since this transformation is 1 to 1. For continuous case, it's more involved. For example, let x be a random variable with a known PDF fx. So I know all the distribution for x. Now I want to know what's the distribution for y. So there are two different techniques we can use. One is called the CDF technique. CDF technique means what? We need to work out the CDF of y directly. Just work out the CDF. So this is a very general technique. Work out the CDF of y. For example, let fx is half. So this is uniform between -1 and 1. So this is a distribution for x. Now that y is x squared. So this is a transformation. I want to know what's the distribution for y. So what's the PDF for y? Now in the CDF technique, I need to work out the CDF of this one. Now probability y less than equal to y. So this is the CDF. Now what is big Y? So it's x squared. So x squared less than equal to y. So x should be between negative squared y to squared y. Since I know the distribution for x, I can calculate this probability. So this is the integration. Now we can get the CDF of y in this form. Once we know the CDF of y, you take derivative, you can get the PDF of y. So that's called a CDF technique. So work out the CDF y directly. There is another technique, it's called the PDF technique. The PDF technique, you should apply this technique only in this special case. The transformation is 1 to 1. So if the transformation is 1 to 1, that means you can get inverse. So I have transformation, I can get the inverse. Once I can get the inverse, I can calculate something called Jacobian. So this is called Jacobian. I take a derivative, take Jacobian. Now I can get the PDF y directly. So PDF y, I just plug in the inverse, multiply the absolute value of Jacobian to make it positive. PDF is always non-negative. Absolute value of Jacobian. You also can show this easily by the CDF technique. So to get the PDF, we get the inverse, we get the Jacobian. We just plug in the inverse into the distribution of x, multiply absolute value of Jacobian. So this is how we get the PDF of x. For example, this is a uniform, x is uniform between 0 and 1. Now I have a PDF, ask you to get the PDF of y is -2 log x. The -2 log x is 1 to 1. So this is 1, 2, 1. The inverse of this transformation, you can get the inverse. So it's x g inverse y is e to the negative y over 2. Now you can calculate Jacobian, take a derivative. So this is a Jacobian. So we can plug in to get the PDF y. So we plug in, multiply absolute value of Jacobian. We can get the PDF y. So this PDF y is exponential distribution. So this is how we apply the PDF technique. Next, let's talk about expectation. First, the definition of expectation. Let x be a random variable. If x is a continuous random variable, the expectation is given by this way. You do integration x fx. Now, the most important part for expectation. So expectation is a number. So this expectation is a number, not random. X is a random variable. Expected value of x is a number. The definition is this integration. So don't forget this x. Otherwise, you always get 1. Similarly, if x is a discrete random variable with PMF, px, you can calculate the expectation of x. So it's a sum, x, px. Expectation is sometimes called mathematical expectation or expected value of x. We can talk about expectation of transformation. For example, let x be a random variable. Y is a transformation. Now, how to calculate the expected value of y? There are 2 strategies. For example, I can get the distribution of y first, then apply the definition of expectation. So this theorem tells you that that's not necessary. You can calculate the expected value of transformation directly. So this is expected value of gx. So expected value of gx is just do integration, gx fx. So this is a distribution of x. Similarly, you can, for the discrete case, this is also expected value of gx. So x is random. So it's gx, px. So this is PMF for x. There is an important property for expectation. Expectation is a linear function. Linear operator, you can think about. Linear means what? A constant you can move out. Expected value k1 g1x plus k2 g2x. So k1, k2 are constant. So if it's a constant, you can move out of the expectation. So it's k1 expected value g1x plus k2 expected value g2x. So constants you can move out. If it's not a constant, you cannot move out. For example, expected value of gx. This is definitely not equal to g expected x. That's not true. You cannot just move g expectation inside. If g is not linear, this is not true. There are some special expectations. The first one is called the mean. For example, if x has this support, so these are the possible values. Expected value of x is just this weighted average. What's the weight is a PMF. So this suggests that expected x is also the arithmetic mean of values of x. So sometimes we call it mean. So let x be the random variable whose expectation exists. The mean value mu of x is defined to be expected value. So this is mu is equal to expected value of x. The mu is called mean, population mean, the mu. That's the notation. The second special expectation is called the variance. So for example, let x be the discrete random variable with this support, the possible values, with PMF. So expected value x minus mu square. The mu is the expected value, mean. So this by definition. So this is a weighted sum. This sum may be interpreted as a weighted average of the squares of the deviations of the numbers A1, A2 from the mean mu. That's exactly the definition of variance. So the variance, let x be a random variable with finite mean mu such that expected value x minus mu squared is finite. The variance of x, definition, is the expected value x minus mu squared. Sometimes you can write sigma squared or variance of x. That's a notation. So that's called the variance. So if you expand this square, you can get a formula to calculate the variance. So sigma square equal to expected value x squared minus mean square. So first square, then expectation. Now this is first expectation, then square. So that's the difference is sigma square. If you take square root, so we get sigma. Sigma is called the standard deviation of x, the standard deviation. The number sigma is sometimes interpreted as a measure of dispersion of the points of the space relative to the mean mu. If the space only contains one point, the point mass k, probability k equal to 1, then mu equal to k, sigma equal to 0. The point mass, the mean is just this number. There is no variability, so no variance. So by the way, sigma square by definition is always non-negative. It has square. So sigma is also non-negative. It's standard deviation. Now the next special expectation is called a moment generating function, MGF. First, what's the definition? MGF, this is the definition. It's a function. It's a function of t. Its expected value e to the tx. What's random? X is random. X is random. T is just argument. So give me a t. I calculate expectation. So that's a number. So make this a function of t. So it's called moment generating function. So when t equal to 0, moment generating function is 1. If x is a continuous random variable, the moment generating function is just this integral. If x is a discrete random variable, the moment generating function is just this sum. So moment generating function is a very powerful function. So it's similar to CDF, PMF, or PDF. If x and y have the same distribution, we know the CDF are same. We also know the moment generating function should be the same. The moment generating function uniquely decides the distribution. Moment generating function, MGF, uniquely decides the distribution. Now, another question, why it is called a moment generating? In fact, it can generate a moment. Now, how to generate a moment? If I take a derivative of this function, evaluate it at 0, first derivative, you will get a mu. If I take the second derivative, you will get a second moment, expected value x squared. If I take the mth derivative, you will get the mth moment. So this is why it's called moment generating function. Now the derivation is also very simple. For example, I take derivative with respect to t. On some conditions, I move this derivative inside the integral. So this is a function of t. I take derivative, so I get x e to the tx fx. Now I let t equal to 0. So I get t equal to 0. I get x fx dx. So this is the expected value of x. Similarly, you can take second derivative, let t equal to 0. You will get the second moment. So you can get any moment. So this is called the moment of this random variable. Here are some references for the probability.